Hello everyone. In this lesson we're going to continue our discussion of improper integrals by considering the domination test for convergence and divergence. Now this is going to be a test that we can use in combination with the P-series test that'll help us to determine if improper integrals of some common functions converge or diverge. So the test makes this statement. If we're given two functions, f of x and g of x, in which f of x is larger than g of x, and they're both bigger than or equal to 0, so their graphs have to lie above the x-axis, for all x bigger than or equal to some fixed value a. Then we have these two statements. If the improper integral of f of x from a to infinity converges, then the improper integral from a to infinity of g of x also converges. Now that should make sense if you think about the graphs of f and g. The graph of g is going to lie below the graph of f, and so if this integral exists, certainly this one will also. Now the second part of this test states that if the improper integral from a to infinity of g of x diverges, then the improper integral from a to infinity of f of x must diverge as well. Now let's take a look at a little graphic illustrating why these two statements are true. Now consider this graphic here. Suppose we have these two functions, and let's suppose that the upper function is f of x, and the lower function right here is g of x. And let's consider these two improper integrals. Now part 1 of the domination test makes this statement. If this integral exists, so in other words, if the area under the graph of f is finite, then certainly you can see that the area underneath the graph of g of x will also have to be finite. And that's all that part 1 is saying. So if this exists, then so must the improper integral of g of x dx be finite as well. Makes sense. On the other hand, part 2 of the domination test makes the statement that if the area underneath the graph of g of x is infinite, well, then certainly the area underneath the graph of f of x must also be infinite, right? That makes sense. And so part 2 states that if this is infinity, if this is infinite, then so must this be infinite or diverge. So that's part 2. So that makes sense. Now let's take a look at a few examples of how we use this. So let's consider this first example. We want to determine if the improper integral from 2 to infinity of x over x to the 4th plus 5 converges or diverges. Alright, so when you're applying the domination test, you have to first of all get a feeling for whether or not your improper integral is going to converge or diverge. And that's going to tell you whether or not you're in case 1 or case 2. So let's take a look at this. If we consider the integrand x over x to the 4th plus 5. Now notice that for x large, the 5 doesn't really contribute very much, right? If x is very, very large, 1 million divided by 1 million to the 4th power plus 5, that's basically the same as 1 million over just 1 million to the 4th power, right? So this is approximately the same as x over x to the 4th for x really large. And this, of course, is equal to 1 over x cubed. Now we know that the integral from 2 to infinity of 1 over x cubed exists by the p integral test, right? Because in this case, the p is equal to 3, which is bigger than 1. Okay, so this certainly exists by the p integral test. So we have a feeling that this is going to converge. All right, but now we need to prove it rigorously using our test. Well, so what we need to do, it seems like we're going to be in case 1. So since we're going to be in case 1, we want to think of this, our integrand here, as being the g of x. Okay, and then what we want to do is find an f of x that is a little bit larger than the g, in which the integral of the f converges. Then we can conclude that the integral of this term converges. Now the f is going to be something like this, some multiple of the 1 over x cubed. So let's see how we can determine what f is. Well, if we take a look at our integrand, notice that that is going to be, we want to go less than or equal to, right? Because we have to try to pick out what the f is going to be. Now, to make the right-hand side here a little bit larger, what I can do is make the denominator a little smaller, right? You know, notice that, for example, 1/8 is less than 1/3. So by making the denominator a little smaller, 3 is smaller than 8, 1/3 is actually bigger than 1/8. So to make the denominator here smaller, I can just get rid of the 5. We'll just throw the 5 away. And so this is going to be less than or equal to x over x to the 4th. Well, that's just equal to 1 over x cubed. So that's going to be the f of x that we're working with. And this was our g of x, what we started with, our integrand here. And so therefore, we can say that since this integral exists, right, so now this is our f, so now we can say that therefore, since the integral from 2 to infinity of 1 over x cubed dx exists, so does this. And we're finished. Okay, so in this case, we thought our integral converged. We had a feeling that it converged. So we thought of the integrand as being the g, and we needed to find the f of x that was a little bit bigger than the g, in which the integral of the f also converged. Now let's take a look at this example. Now here we want to determine if this integral converges or diverges. Now let's take a look at the integrand here and get a feeling for whether we think this should converge or diverge, and then we'll prove it using our test. Well, if we look at notice that for x very large, this is going to be approximately the same as the square root of x over x, right? The 1 and the 2, for x really large, you can basically throw those away, right? And make the statement that this would approximately be equal to root x over x, which of course is 1 over root x, and that's for x large. Okay, now we also know that the integral from 1 to infinity of 1 over root x, that diverges, since in this case the p is equal to 1/2, right? So this diverges by the p integral test. So we think it seems reasonable that this should diverge also. So we think it diverges. All right, well, to prove it rigorously now using the domination test, what we want to do now is we want to consider ourselves as being in case 2. So we want to think of the integrand here now, this, as being the f of x, and we want to find a g which is a little bit smaller than it, in which the integral of the g diverges, then we can conclude that our integral down here will diverge as well. Okay, so to do that, if we consider and now we want to find a function which is a little bit smaller than our integrand. So now what we're going to do here is to make this over here a little bit smaller and not affect the powers of the x's that are appearing. Notice that we can eliminate this 1. So certainly this will be bigger than or equal to the square root of x over x plus 2, right? Just make the numerator a little bit smaller. Okay. Now what I want to do is make the denominator a little bit bigger. See, if I make the denominator bigger, but I don't want to affect the power of the x appearing down here, well, then what's over here will be a little bit smaller, right? Okay, you know, if we look at 1/3, that is going to be bigger than 1/8, right? You see, I made the denominator larger. Well, what we're going to do is replace the 2 in the denominator, right there, with a 2x. Okay, remember the x is supposed to be bigger than or equal to 1, so certainly that's true. And then this is equal to root x over 3x, which we can write as 1 over 3 root x. Okay, and now since the integral from 1 to infinity of 1 over 3 root x dx, well, you can just pull the 1/3 out in front, right? So certainly this is equal to well, this integral diverges. Since the p in this case is 1/2, which is less than or equal to 1. And so by the p integral test, this diverges. And since this is smaller than what we started with, we can conclude that our integral over here will, in fact, diverge. And there you go, we are finished. All right, so you would say just down here, if you wanted to complete this, therefore the integral from 1 to infinity diverges by the domination test. And that's it. Now here's an interesting example we're going to look at. It's called Gabriel's horn. So this is an example of a shape that has a finite volume but infinite surface area. So for this shape, we take the curve y equals 1 over x, that we have pictured right here, and then we take the region underneath the curve from 1 to infinity. So that's this shaded region that we have right here, and we rotate it around the x-axis. So it will form this horn shape that we have down here. You see this? That's what it forms. Looks sort of like a trumpet horn. Now we're going to show that this shape has a finite volume but infinite surface area. Now for the volume, we're just going to use the disk method, right? So we just think of taking a little disk right here, or washer. Now this is located at position x. We'll call that radius y. And remember, our volume formula for the disk method is going to be pi integral, and in this case it's going to go from 1 all the way out to infinity. See, this x slides from 1 to infinity. The outer radius is y squared minus the inner radius, well, it's always 0, right? Dx, right? This has a little thickness here, delta x. And now we have to put everything in terms of x's, so this is going to be pi integral 1 to infinity 1 over x, that's the y, squared, right? We square that, dx. And so then this is pi integral 1 to infinity 1 over x squared dx. Well, by the p integral test, we know that this converges, and it actually converges to pi times the integral. Remember, by the p series test, it's going to be 1 over p minus 1, where for this integral here, the p is 2, and so this is going to be pi times 1 over 1, or just pi. There you go. So the volume of this shape down here, what's inside that horn shape, is pi, has a volume of pi. Now the surface area. Okay, so remember that formula. So we're going to have 2 pi integral. Now what we have to do is think of a little frustum right here, say just a little frustum that is being formed right there. Now the radius there is going to be y times square root 1 plus dy dx squared dx. And this goes from 1 to infinity. And so now this is going to be 2 pi. The y, of course, is 1 over x. All right, now the dy dx. So just going back to this equation right here, of course, y prime is negative 1 over x squared. Okay, so when we put that in here, we're going to get 1 over x to the 4th dx. All right. Now, finding an antiderivative for this is rather difficult, but we don't need to, because we can prove that this integral does not exist by using the domination test. So now notice that if we look at the integrand here, we'll notice that that integrand for x very large, this is just going to behave like 1 over x, but the square root, as x gets really large, this is going to go to 0, right? And we're going to be left with basically the square root of 1. So the integrand here is going to be approximately 1 over x for x very large, and we know that the integral from 1 to infinity of 1 over x diverges by the p integral test because p is equal to 1. So we have a feeling that this is going to diverge. And to prove that, now what we can do is this, since we have a feeling that this diverges, so if we take this integrand, and by using the domination test, what we want to do is this. We want to find a function that's a little bit smaller than this one, in which the integral from 1 to infinity of that function that we get over here also diverges. And then that will prove that this diverges as well by the domination test. All right, well, this one's not too hard, because all we have to do is write this. See, this is certainly going to be true. You see, 1 over x times the square root of 1 plus 1 over x to the 4th is going to be bigger than or equal to 1 over x times just the square root of 1. You see, if we make what's in here a little bit smaller by just throwing this number away, we get this. Now we know that the integral from 1 to infinity of 1 over x, right, this square root of 1 is just 1. We know that this diverges. And so therefore, the surface area integral, this integral down here, will also diverge. So the surface area is infinite. So that's an interesting shape. This shape down here has a finite volume, yet an infinite surface area. Now there's sort of a paradox that people point out with this shape, but, well, it turns out it's not really a paradox, but you might think initially it is. So since this has a finite volume, we could take a finite amount of paint, tip this so it's upward like this, right? Tip it like this. And since the volume is finite, it seems like we should be able to pour a finite amount of paint in here and fill it because it has a finite volume. But if you fill it, don't you also paint the inside of it? But the inside is supposed to have an infinite surface area, so how could you paint it with a finite amount of paint? Well, as it turns out, there's not really a paradox there, because if you realize that paint is comprised of very, very small atoms, of course, right? Molecules, okay? Well, eventually, this neck down here would become so small that even the molecules of paint wouldn't be able to fit through them. And so the paint couldn't really continue all the way down to infinity. So in reality, the paint would get stopped somewhere in this horn down here. And so you couldn't really fill it all the way to infinity and at the same time coat the sides with paint. So that's why there's not really a paradox there. And that concludes our discussion about the domination test with a few examples.